Okay, so I have started sharing the screen. Can you guys see the screen?
Yes, bhai.
Okay, so we'll be starting off from here, amplitude modulation. That after the last thing that we finished in our last class was this. This is the last topic that we'll be covering from this chapter, FT properties. And after that, we'll be, even though there are some things remaining after this, like DTFT, then Parseval's relation, but those things are not included in the syllabus. And we'll be moving directly to the next chapter, which is Introduction to Digital Filters. Today, today's class will be relatively short, I think, because we'll be only covering the introduction of digital filters, some basic theoretical stuff. Okay, so let us start. So amplitude modulation, this was the last topic that was remaining. One of the Fourier transform properties. Okay, so what is amplitude modulation? If you remember, in one of the previous chapters, in a few of the previous chapters, we have already said this thing, that convolution in one domain corresponds to multiplication in the frequency domain. So this amplitude modulation is actually the reverse. Here, instead of what we just said here is that convolution in time domain, in one domain, actually, usually what we're saying is in the time domain. Up until now, we have always been saying convolution in the time domain and multiplication in the frequency domain. Now think of it in the reverse way, convolution in the frequency domain. Okay, for that you would have to do multiplication in the time domain. So whatever intensity values you have in the time domain, if you just, instead of performing convolution operation, if you just directly multiply them point by point, a0 with b0, a1 with b1, if you just multiply them point by point, what you get is just this operation is known as modulation. Okay, amplitude modulation. So if you can already guess that since you are just multiplying in the time domain, in the frequency domain, you would get the convolution operation automatically. But that is not our concern. Here we are not thinking about what will happen in the frequency domain. We know that there will be convolution, but we are not concerned with that. We are only concerned with the multiplication in the time domain. In the frequency domain, the convolution that will happen, you can already guess how complex that would be. Because first of all, convolution in the time domain was already a complicated operation. There were two loops, two nested for loops that are used to do this kinds of operation. And now here in the frequency domain, if you had to do convolution, you'd be multiplying and adding a lot of complex numbers. So you can already guess how complex that would be. So we are not thinking about that, what will happen in the frequency domain. Here we're thinking about just the multiplication in the time domain. Okay, so this is the main point here, multiplying in the time domain, which is actually the reverse of this one. Okay, so now this will give us an example of, this will show us an example of negative frequencies, how negative frequencies come in, okay, into everyday applications. So, okay, so modulation is what I just said right now is that modulation is just multiplying two signals in the time domain. But in theory, it is actually just merging two signals to form a third signal with the desirable characteristics of both. So the thing is, why do we actually need to multiply and not convolute? When will we need to modulate and not convolute? That you will understand in this scenario. If you look at this scenario, what they basically say is that audio signals, for example, my speech, or when you talk, when someone speaks. So they when we produce the audio signals, those are of short wavelength. Yeah, those are of short wavelength. That means of high frequency. Okay, so if wavelength is short, that means frequency is high, right? You guys already know this stuff from intermediate physics. Okay, so the other scenario that could happen is that you could have a long wavelength. That means that corresponding wave's frequency would be low, right? So what kind of wave are useful in what kind of scenarios? Probably guys already know that for a signal that would travel a long distance, that particular signal's wavelength needs to be what? Does anyone know? Should it be short or high?
High.
Yeah. So this is the one that you need. The high wavelength, low frequency. This is the one that you need. And that is why radio signals are used for communication. Okay, radio, sonar, all of those signals are of high wavelength, low frequency. Okay, so that is why they can travel long distance without their quality getting degraded. But short wavelength signals such as X-rays, gamma rays, then for example my speech or anyone's speech, those are of high frequency, short wavelength. They do not travel far. They degrade exponentially over distance. Okay, and gradually they lose their values, the intensity, amplitude values, and cannot be received in a faraway location. So that is why what we need is, but think of this scenario. We are trying to uh, send a message, that means a voice, to a great distance, somewhere far away. So for that, we are trying to send a message, but we are also trying to send it far away. So we need characteristics of both. We are trying to send a short wavelength signal in such a way that it behaves like a long wavelength. That means it is not degraded over long distances. So how can we do that? How can we get characteristics of both? So this is what modulation achieves. When you multiply two signals, you get desirable characteristics of both. And that is why we perform modulation. So this is just the basic understanding of its application, why we needed it, why this operation is needed. Okay, so you can go through this example and you'll understand. This is basically that particular scenario that I just described. Okay, so here an example is shown of amplitude modulation in both time and frequency domain. 1014, if you look at this figure, you'll see there are two things here. One is the audio signal. Suppose this is someone's speech, and this is the carrier signal. Notice that this audio signal has low frequency, and this one has high frequency. This carrier signal has high frequency. Okay, so and also notice that in figure A, this is the one with the audio signal. If you look at this, it also has a bias. This one is a general signal, something that has a particular high frequency and is normalized at 0. As you can see, it is oscillating around 0. But this one, this audio signal, it has a particular DC component. It is a bit above 0, above the equilibrium, and it has a particular combination of frequencies, not just one frequency. It is a combination of frequencies. So that is why it is not a pure sine wave nor a cosine wave. So that is why it looks like this. So if you perform DFT on it, you would get this. Because of the DC, because of the shift from 0, you would get a spike here at 0. As you can see, there is a spike here. And also, due to the combination of frequencies that it contains, you would get a bunch of spikes from 0 to 5. If you combine them together, it would be a continuous curve like this. Okay. So there are a bunch of spikes. That means you can consider that there are lots of frequencies in between this range. And now also you have a carrier signal, and this one can also be made to go through DFT, and you'll get a spike here at 30. It's actually in kilohertz range. These are all in kilohertz range. Okay, so this is what it says. The actual values are already described here. That figure B, this one, the carrier signal, this one contains a frequency spectrum that is composed of frequencies from 300 hertz to 3 kilohertz. And this one is needed for voice communication, plus a spike for the DC component. And all other frequencies have been removed by analog filtering. Okay, so figures C and D show the carrier wave. Okay, oh, so this one is for, this is figure B, not this. C and D is for carrier wave, and A and B is for the audio signal, the speech signal. So here you have the time domain. In B, you have the frequency domain. This is showing the values, the actual values of frequencies that are present here. So the actual values are from 0.3 kilohertz to 3 kilohertz. So this is the range from 0.3 kilohertz to 3 kilohertz. This is the range of frequencies that are present here. And in C and D, you can see the carrier wave, which is a pure sinusoid of much higher frequency than the audio signal. Okay, so when you perform modulation between them, by modulation we mean just simple multiplication in the time domain. In the frequency domain, we are not thinking about what will happen in the frequency domain, because mathematically this will be very complex, because these are all complex numbers, and we are performing multiplication of complex numbers and then adding them. So we are not thinking what will happen here. We are just performing multiplication between them. What we will get is something like this. And notice that what actually happened here is that this higher frequency got enveloped. That means its shape got defined by the lower frequency. So this is what will always happen when two signals are multiplied together, point by point. What happens is the higher frequency signal gets shaped by the lower frequency signal. So notice that this higher frequency signal got shaped. Its shape was defined just according to this shape. If you outline this line over this, you'll see that this is what you are supposed to get. Okay, and it will be on both sides actually, since this is oscillating on both sides. So you'll see the shape here as well in a mirror fashion. So this is basically what will happen every time you modulate. Whichever one is the higher frequency, you will see mostly the higher frequency oscillation, and its shape will get defined by the lower frequency. And now what will actually happen in the frequency domain, we are not thinking about what happened by the multiplication and addition, but whatever will happen at the end is something like this. Whatever pulse you got here, and that pulse would appear at this particular location where you got the spike. So here there was a spike, and here there were multiple spikes, and all of this will get copy pasted at this location. So, and this will also get mirrored. So this is just at 0. It does not matter if we mirror it, but this is on the right side of 0. So if you mirror it, it will go to the left side. Okay, and all of this thing will get copy pasted at this location. So this is what you will get in the frequency domain. How it came, that is not of our concern, but this is basically what we will get. And here there are some important things to notice. That is the middle one. This one refers to the carrier signals frequency. Okay, so this one was the carrier signals frequency. This is where we will get the carrier signals frequency at this particular location. And there will be an upper sideband and also a lower sideband. The upper sideband, this is coming from the audio signals, the audio signals frequencies. There were multiple frequencies here. All of them are coming here on the right side. Those are called the upper sideband. And on the left side, there will be those same frequencies again in a mirrored fashion. That will be called the lower sideband. Okay, so these are the three things that we get, the three components that we get in the corresponding frequency domain. And now each of these components correspond to three different things. Okay, so the first one, the DC component. So this one, this corresponds to just the zero here, the whatever amplitude we got here for the 0th frequency. This is the part we will get here. And then the upper sideband, this one refers to the positive frequencies from 0.3 to 3 kilohertz that were present here. So this one had positive frequencies from 0.3 to 3 kilohertz, as you can see here. This one will appear in the final convoluted frequency domain in the upper sideband. And in the lower sideband, there will be the negative frequencies between minus 0.3 to 3 kilohertz. By the way, if you're wondering why 0.3 to 3 kilohertz, you can look at this particular thing here, figure B. This showed the frequency spectrum of the audio signal, and it contained frequencies from 300 hertz to 3 kilohertz. 300 hertz means 0.3 kilohertz. So that is what we are getting here. The right one will give these frequencies, and the left one will give these frequencies respectively. And even though the negative frequencies in the original audio signal are not directly seen, so in here you do not see any negative frequencies, because that is how our DFT algorithm was defined. If you remember DFT, we were running loops from 0 to n by 2 plus 1, or if you perform FFT, there will be 0 to n, that many frequencies defined, and these are all positive. Notice that there are no, the algorithm does not compute the negative frequencies by itself. But if you perform convolution, it will get some frequencies on its left side as well, and those frequencies will be the mirror of the positive frequencies. So these are actually the negative frequencies that the algorithm directly does not compute. So you could consider that there were negative frequencies here, but the algorithm did not compute them. Okay, so there were negative frequencies here, but the algorithm FFT, neither FFT nor DFT will actually compute the negative frequencies. It will store only the positive frequencies. But when you perform modulation, and in the corresponding time frequency domain, if you perform convolution, you will see that there actually were the negative frequencies, because how else are they appearing here, right? So this thing got copy pasted here. Then how did we get the left part? That this left part actually came from the negative frequencies that were present here. If you take all of them together and copy paste them at this location, then only you would get this thing, right? So this one shows that there actually were some negative frequencies, but at first those were not present because the FFT or DFT did not compute them. So this is all about modulation and where it is actually useful. Like I said, mostly for sending signals to faraway distances, such signals that would not actually travel faraway distances. So we are modulating them together with signals of different characteristics, and then we are doing such operations, such applications. So there are lots of situations where this is useful, such as radar, sonar, and some in some medical applications as well. So that is all about Fourier transform properties. The rest of the things from this chapter are not included. That is, there are some other things remaining, such as discrete time Fourier transform (DTFT), and then Parseval's relation. So these things are not included. You can skip through them. We'll be moving on to the next chapter and trying to cover the first part of digital filters. So let us start with the new chapter. So digital filters, what are they? Digital filters are, we have already talked about convolution, right? In one of the previous chapters, in chapter 6, yeah. In chapter 6, there was convolution. What were we doing there? We were taking an input signal, we were performing some operation, which we discussed already before, with some impulse response. And that impulse, due to that operation, we got some output, right? So digital filters are basically systems that have some predefined impulse response. So here, impulse response is the main idea here. So different kinds of impulse responses will net us different kinds of outputs, giving some specific characteristics to the outputs. Suppose in the previous cases, what we did was we just took this impulse response to be some random signal, and then we performed convolution and we got some output. But now what we are saying is that this won't be just any random signal. This will be some well-defined signal, which and because of some well-defined signal, we'll get some well-defined output. Okay, so different kinds of impulse responses will give us different kinds of characteristics in the output. For example, reduce the blurriness or increase the sharpness, different kinds of things we might get. Okay, so there are two general purposes for digital filters. One is the separation of signals that have been combined, and the other is restoration of signals that have been distorted in some way. And both of them are actually performed using convolution in time domain or multiplication in the frequency domain. But only the thing that will differ in these two applications is what kind of impulse response you're using, or in the corresponding frequency domain, what kind of frequency response you're multiplying with. Okay, so as we have already said, these are the two uses: signal separation and restoration. So separation is needed when signal has been contaminated with interference, noise, or other signals. For example, suppose in a medical application where you are trying to measure the heart rate of someone, of a mother, and the mother is also pregnant with a baby. In that case, you'll be getting two separate signals. When you try to measure the signal of only one person, you're actually going to get a combined signal. So that particular combined signal needs to be separated out. So with some pre-established knowledge that usually this is the range for babies and this is the range for adult people, you can use some kind of algorithm to separate out the combined signal. Also, in case of signal restoration, this is needed when the signal is distorted in some way. An example of this application is when an audio recording made with poor equipment, you can make it go through a filter to add some artificial effects to it. For example, echo, reverberation, and all these things. Okay, and also if you think in case of an image, in terms of a 2D signal such as image, in that case, you can perform a deblurring of the image or reduce the sharpness, or whichever one you prefer. You can make it go through a filter, and that filter will give such characteristics to the output. Okay, so in case of digital filters, how are we going to talk about them in terms of signals? So basically, what we will do is we will think of the both of the input and output signals in the time domain, because signals are usually created. This is just to make it simpler in case of the for our discussion. Usually, it is very easy to visualize the time domain than the frequency domain, and we direct normally as humans we directly measure signals by sampling them after at regular intervals of time. But this is not the only way of sampling. Okay, so the second most common way of sampling would be at equal intervals of space. For example, usually for sound, what we do is we measure sound by taking intervals along time, right? So the horizontal axis is time, and we take some intervals along time, and we have some particular amplitudes at different points, right? There could be another way of taking samples and generating a signal, and here they're saying that particular thing is space. So what do we mean by taking samples along space? That would be very clear if you think about how a line follower robot or any kind of machinery that takes samples using sensors, IR sensors, infrared sensors. So they might generate a signal by using sensors placed at particular space intervals. Okay, some XY. After a particular XY, so along X you can have x-axis, and along y you can have y-axis. So you can define a signal at some particular xy. There was some particular amplitude. You can have a value here. Also, at another particular xy, you could have another value. At another particular xy, you could have another value. So sensors is any kind of machinery that uses sensors to measure something and then generates a signal using those values. That is an example of such a scenario. Okay, so this is just another way of representing a signal other than time. So as shown in figure 14.1, here, you can see that every, this is figure 14.1 here. So you can see that every linear filter has an impulse response, a step response, and a frequency response. All of them are actually shown here in this particular figure. This is the impulse response. For now, we are not caring about what this filter is going to do. We are just seeing what its impulse response looks like, what its frequency response looks like, and what its step response looks like. Okay, so now all three of the representations are important because one of them, each of them may be used to describe some particular behavior in some domain. Okay, so the most straightforward way of using a digital filter is by convolution. So as I've already said before, one way you can think of digital filters is that you're just defining some H, some impulse response that you're convoluting with. So if you take a signal and make it go through a filter, that particular, what you're doing is you're taking that signal and you're convoluting with some predefined H. For different kinds of H, you'll have different kinds of filter effects. So this H is everything for a filter. By H, I mean the impulse response. Okay, so when you use a filter used in this way, that is using convolution with an impulse response, that particular H or filter or impulse response is known as the filter kernel. Like this is like the main important thing for that filter. So this H or the impulse response is known as the filter kernel. And also there is another way to perform filtering other than convolution. That way is known as recursion. And we haven't talked about recursion before, and actually that is not necessary even for this chapter, but just know that there are filters that use this procedure instead of convolution. They use the recursion procedure, where recursion is basically an implementation of filter where you're performing convolution, but each sample in the output is calculated by weighting the samples in the input as well as, okay, so this was for convolution. For recursion, what you would do is you would use some value from the output as well. Okay, so this is how recursive filters are implemented. This is an extension, okay, of the previous convolution method. In case of convolution, you just use the input values and the impulse response. But in this case, what you do is you use the input values as well as the output values, previously calculated output values, to calculate the final output. So instead of using a filter kernel, the recursive filters are defined by a set of recursion coefficients. And this type of filters are known as recursive filters, as it has already been shown here. So this type of filters are known as recursive filters. And the previous filters were known as filter kernel or convolution filters, in other words. Okay, so the important thing to just see, remember here is that all linear filters have impulse response, even if you do not use the impulse response to implement the filter. That means even if you use a recursive filter, that recursive filter also has some sort of impulse response. Probably we are not using the impulse response. In this case, we may be using some recursion coefficients to define the filter, but still it has some hidden impulse response. So every filter basically has some impulse response, whether you use it or not. Okay, so the impulse response of recursive filters are composed of sinusoids that exponentially decay in amplitude. So here we are talking about recursive filters. We are saying that we are not, in case of recursive filters, we are defining them using recursion coefficients, but they will also have some impulse response, right? So what we're saying is that impulse response will basically be sinusoids that exponentially decay in amplitude. So in principle, this makes their impulse response infinitely long. Okay, so if we are saying that there is impulse response is basically a sinusoid, sinusoids are infinite signals, right? So that means their impulse response would be, in theory, infinitely long. However, the amplitude eventually drops below the round off noise of the system. So here, as you can see, this is an example of recursive filter. Its corresponding impulse response would look something like this. This looks like a sine wave that gradually became exponentially got close to zero, to the left and right. So this is an example of a recursive filter. And in this case, what we normally do is, even though this should be in theory infinite, the impulse response should be in theory infinite. But when we store them in a digital system, we store only a particular window of it. So in this case, they are storing only this particular window. So that particular window can be defined using your noise threshold. At what particular point you consider this thing to become very close to the noise. So your noise is something very small, right? So if the impulse response itself becomes so small, the amplitude values become so small that they get close to the noise, at that point you can define your window. That means the values after it do not matter to me. So you can take a window of this length and consider it as your impulse response for the recursive filter. So even though we are taking a window, remember that in theory, the impulse response should have extended towards infinity, both towards the left and right. So that is why they are also known as IIR filters. That means infinite impulse response filters. So IIR stands for infinite impulse response. So that is why recursive filters are known as IIR filters. In comparison, the previous type of operation, that is convolution, any filter that you design using convolution, those are known as finite impulse response filters, or FIR filters. So our discussion will be mostly on the FIR filters, because convolution is basically what we are concerned with when we are performing filtering. Okay, so, and the step integral of the, okay, so another thing is that how are the step response? So this is the step response and this is the impulse response. So how are they related? So if you look at the figure, you can already see that you can move from one to the other by this operation. So integration, so impulse response is basically the derivative or differentiation of step response. Or in other words, step response is the integration of impulse response. If you're wondering how this can be the case, how can impulse response and step responses be related using integration? You can think of it in this way. What is impulse response? Impulse response is what happens when you send a unit impulse. You guys already remember what a unit impulse is, right? As amplitude of 1 at 0. This is what a unit impulse means, or a delta function means. So impulse response is when you when you send this through a system, whatever the system produces, that is its impulse response. Okay. So, and step response, the step signal would have been something like this. You would get 0 in all negative points, and at exactly 0 you would get a 1, right? And after that, in all the positive points, you're going to get that same amplitude. So this is a step signal. It would be 0 before it, and at one particular point it would become 1, right? It would become 1. So now you can think how this can be gotten by performing integration on this particular signal. So what do we mean by integration? If you remember, integration means every value would be the previous value plus the current value. So the corresponding integration of this would be produced by taking current values, summing it up with the previous value. Okay, so the previous values here were all zeros. So the corresponding integration value here would be 0 plus 0. So it would be 0 here. 0 plus 0, it would be 0 here. And then 0 plus 1. So the previous value was 0 and the current value is 1. So the integration value would be 1 here. Okay, and then the previous value is 1 and the current value is 0. So the integration value would be 1 plus 0, 1. So again, it would take the previous value, that is 1 plus 0. So the integration value would be 1. So as you can see, if you integrate this, the corresponding integration values would be exactly equal to this, the step signal. So this is how the relation can be understood, how impulse response can be correlated with the step response. So basically integration is the thing that transforms a impulse response to the step response. Okay, so this is what is said here. The step response is the integral. The step is the integral of the impulse. So similarly, the step response is the integral of the impulse response. So whatever I just showed is that I took a step function, I took an impulse function and I performed an integral on it by summing it up. Every point was summed with the previous point, and that's how I got the step signal. So you can just summarize that the corresponding responses of them, that means when you pass them through a linear system, the resulting thing would also be linearly maintained, right? The characteristics would be linearly maintained. So if one is the integral of the other, the responses would also be the integral of the other. So this is basically what it says. So this provides us two ways to find the step response. One is to feed a step waveform into the filter and see what comes out. So this is the basic definition wise. So what do we mean by step response? For impulse response, we said that what a system would produce if we feed a delta function to it. So similarly, what would be the step response? What the system would produce if we feed a step function to it, a step signal to it. So this is one way to see it by definition. And the other is, instead of feeding a step function, we just know the impulse response and we integrate it. So these are the two ways to think of a step response. And also another thing to clear out here, they are saying integration. I also said integration multiple times, but what I actually did was I performed running sum. I did not actually do integration. Integration is only applicable for continuous signals. And what I'm doing here, what I just did there, this particular formula, every point would be found using the previous point and the current point, xn. Okay, so that particular formula, this is the formula for running sum, not integration. Here I'm only considering discrete points. So this is just some theoretical thing to worry about. That is, we are using the running sum here, not the integration. Okay, so the next thing is this particular thing, the frequency response. If you notice here, in this figure, the frequency response was also shown using different kinds of unit, that is in decibel. So why is that? Both of them have some uses. One is used in one kind of scenario and this is used in another kind of scenario. So we'll be saying in which kind of scenario one is useful and which is useful in the other scenario. But if you notice in this kinds of notation, we would need to think about the decibel, right? This new kind of unit, bell and decibel. So that is the next part of our discussion, bell and the relation between bell, decibel, and all these things, what they mean. So this will be the topic of our next classes discussion. For now, this is all. This will be all for our today's class. I'll be ending the class here today. I'll be stopping the screen share now. Okay, so is there any problem with today's topic? Anything you guys did not understand or you want to discuss? No, any question? No question from anyone?
No, sir.
Okay.
No.
Yes. Did anyone want to ask something?
না ভাই কোশ্চেন নাই বলছে
আচ্ছা
ভাই আমার একটা প্রবলেম হয়েছে আমি এলএমএস এ ঢুকতে পারছি
এলএমএস এ ঢুকতে হচ্ছে
ভুলে
না
গেছি
আচ্ছা
বাট
ওয়েট আমি এখনো রেকর্ডিং চালাচ্ছি আমি রেকর্ডিংটা স্টপ করে